because this is our frequency of interest, omega, when omega equals 2. So at that point, omega equals 2, what we're actually trying to do is we're trying to make a shift. When you look at the table, it shows you that this, as a pole, will make a shift from 0 to negative 90. Let's see, where's that? So the pole, this line right here, says, okay, you go from 0 to negative 90. And you pass through the negative 45 degree point, right, halfway, at the pole. So you have to look at your construction line, and you say, okay, for this piece, my frequency of interest is 2. So here's my frequency 2. I need to go through negative 45 at 2, and that line does. And then I just make a slope that goes 1 decade to the left and 1 decade to the right. And so 1 decade to the left of 2, I should be back at 0. 1 decade to the right, I should be approaching, the 20. Yeah. I should be at the negative 90. So that's this blue construction line right here. Then I look at the 10, and I have the same thing, this one right here, the pole of 10. So here's 10, and again with that pole, I should be saying, okay, at negative 10, or at 10, sorry, I should be at negative 45. So that's this point right here. And then that blue construction line should go 1 decade to the left, which is 1, 1 decade to the right, which is 100, right? And connect those all together. And then I just add them up again, right? So I'm starting here at 90, I move along to my first tilt in a construction line, and now I start going down along this line. So this slope here matches this slope here. This gets a little trickier because now here I find another point where this slope is also going down, so it doesn't cancel out, but it makes me go down faster. So this slope plus this slope, I'm moving down at that rate until I hit my next turn point, which is where this blue construction line ends. So then I slow my ramp, and then here, again, now there's the last corner point, and now everything is equal to negative 90, right? And so I'm down at that final phase. So sketching the phase is a little bit less intuitive, I find, than sketching the magnitude. But it's not really any harder, except that your slopes don't always add up as nicely. In these magnitude plots, you typically are dealing with plus or minus some multiple of 20 dB per decade. So you can kind of just count how many times you've gone up or down, and you sketch it. But even so, you can see roughly, even if you didn't get the slopes perfect, which is okay, you know you're starting here at 90, and everything's sloping down to negative 90 at some later frequency after 100. Right? So you could just kind of draw a little swoopy S, and it might not be perfect, but again, you would need to smooth these corners anyways, right? So I would just look at these construction lines and I'd say, well, yeah, I'm going to start here, I'm going to start to drop off when I hit the first corner, and I know I have to hit negative 90 by the time I hit this final corner. So I'm just going to go like that, right? Hand sketch, it's fine. And then I have a behavior. I also know that not only as my frequency goes up, do I pass through a sweet spot, where in fact, if you notice, in this case, at sort of the peak of my sweet spot, right in here, that's also the spot where I have no phase shift. Right? I'm getting the most input power into my output power. Right? There's the best transfer of power. Just like impedance matching. Right? And then as I increase the frequency, so here at low frequencies I have a 90 degree phase shift, right? There's the least match between the incoming and the outgoing power. And then again, at the high frequencies I have the least match possible. They're completely 90 degrees out of phase with each other. But now on the other side, right? Now it's a negative 90 phase. So, again, this gives me a rough idea in a relatively quick fashion. I know that doesn't seem fast. But once you practice just a little bit, you can very quickly look at a transfer function like this, and I would just, I can look at that and I can say, well, I know that there's a 0. I know that there's a 0 through the origin. I know that there's 2 poles, right? And so I would just sketch this. I'd say, okay, I know one's going this way, one is going, something like this, one's going something like this, and yeah, so this is going to, and there's a constant, right? I draw my construction lines, and I say, okay, these equal, so I'm going to be increasing in some way, and then I'm going to hit a corner, I'm going to go down, I'm going to go down more, and I can very quickly say, I may not know exactly where it's happening, but I can very quickly see the rough shape. That's it. I mean, like, it really is. Like, when you look at the transfer function, you just start to think about that is that. And graphically, I can understand the transfer function a lot easier than by the math. Because if you ask me what's happening by looking at this and I try to interpret the numbers, it can be pretty tough, right? Because how this one and this one, how their little lines overlap and where it causes the bump to happen and things, it can be kind of tricky to figure out. So that's why it's always nice to move to this graph and show it. How many of you have used a parametric graphics equalizer on your radio? No? None of you ever play with like the bass and the mid and the treble settings on the radio in your car?
I know called that, yeah.
Yeah? Okay. Have you ever had one that's actually graphic? It actually shows you the little like shape.
Oh, okay.
Fancier ones often than in your car. Most cars only have bass, mid, and treble. But you know, some of them have this really fancy, like, you know, there'll be lots of little like lines, and they'll do something like this, right? Anyways, you know, and you can like adjust. I draw that very well, right? You can adjust very finely all along this. And you kind of make this picture of what you want the sound to look like. And here's your low frequencies, and here's your mids, and here's your highs, right? So if you really like your bass pumped up, right? You like to make your car thump as it goes down the road, right? Or you like to blow your neighbor's windows out when you're in your house or something like that, right? You turn your bass way up. So you like to crank that up, right? And then you don't maybe like the screechy, high-pitched stuff, so you turn that down. This is your transfer function of your amplifier in a graphical representation. That little thing right there that you're actually adjusting, when you're actually adjusting the bass, the mid, and the treble on your radio, you are actually adjusting the transfer function. This is the Bode plot. The thing that they actually show you when they have the graphical ones, it is the Bode plot of the magnitude. They don't worry about the phase. Again, our ears are insensitive to phase, more or less, right? We're much more sensitive to intensity. So that little graph like that bass, mid, and treble that you're used to thinking about in your music, right? And again, depending on the kind of music you're listening to, you might want the bass or you might not. If you're listening to people talk, you often raise the mid and lower the bass and the treble because you want to get that range of human voice, which is around 8,000 hertz. You know, you want to boost that a little so you can hear it more clearly. That's a Bode plot. So you probably are saying, well, I know what that is. Why didn't you just say that at the beginning, right? But, you know, they don't go so complicated, right? Yet that, you graphically, you see that, and you immediately understand what it's trying to do, don't you, on your radio? And you hear the difference. When you crank up that low side and this peak goes up and you hear the thump, 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 you immediately understand what it's trying to accomplish. And that is what we are doing now, but for far more complicated, in some cases, far more complicated systems, right? We're looking at circuits now, and we want to understand graphically what they're doing. So this is great to be able to do it by hand. Again, it's a quick way. You get a rough sketch. I typically wouldn't worry very much about refining these sketches. Like they'll show you in the book that if you have a quadratic pole, like, you know, one that can't be written in this way, but one that has a complex conjugate, a pair of complex conjugate poles, you have to do with the quadratic function. You know, they'll show you, oh, well, at this little point right here, it doesn't just do this, it actually does this. It makes some funky little bump. And you have to figure out, well, how big is the bump, or flat is the bump? That's really complicated. And I'll be honest, you know, like, let's see if they have an example of it. I don't even know if they showed one. They may. Well, at any rate, it's on the table. They don't show that refinement. You'll see that next year in systems and signals. And when you have a complex pole like this, not only does it drop, but there's a little hump that you have to add in. You know, that's way too complicated to try to do by hand in most cases, right? So most of the time, if you want to do that, I would say go to MATLAB. So let's look at this and how we might put that into MATLAB, because it'll give you a perfect output every time. So why not, right?